Thank you so much for your introduction, and thank you, colleague, for your interest in this topic. The title of my presentation is The Curve-Shaped Anchor for Durability and Efficiency Improvement of Piezoelectric MEMS Harvester. This is the outline of my presentation. I will start it with short introduction on the energy harvesting by the MEMS harvester, and then I mainly focus the current challenges in the piezoelectric MEMS harvester. Then I will introduce the fatigue lifetime. To increase the lifetime of devices, I will propose the new anchor shape for the piezoelectric harvester, and also I have some results. Finally, I will finish this conclusion. So let's start it with the introduction. So there are many different sources in the ambient that can be used for the vibration, such as the airflow, human motion, the waves. And this harvested voltage can be used for the sensing and actuating in many different applications, like implementable devices, wireless sensor node, and nanorobotic, so on and so forth. So in order to convert the vibration to the electricity, there are 5 different methods. So electromagnetic, electrostatic, turboelectric, magnetostrictic. Of course, each technique has own advantages as well as disadvantages. However, in the MEMScap, the piezoelectric based seems most promising method because of 2 reasons. First, easy of application by the regular micromachining process, and secondly, high power density of this conversion method. So, if you take a look at on the literature, there are many approaches to increase the efficiency of the devices. One of them is the stress optimization by providing the new structure, and another one is using the multimodal behavior by providing the uniform mass distribution across the cantilever. And very well-known method is using and tuning the proof mass to increase the efficiency and, of course, reduce the resonant frequency. So the main challenge is if during the literature, the designers only consider the 2 objectives. First, increase the efficiency, and secondly, reduce the resonant frequency. However, the main idea of using the energy harvester is to increase the lifetime of the electronic application. So the energy harvesting system itself should be operated for the longer period than the regular battery. So the motivation of this study is first, investigate the fatigue damage of the silicon-based energy harvester, and then propose the new mechanical structure for MEMS harvester to first improve the energy conversion efficiency, secondly, reduce the resonant frequency, and of course, enhancing the lifetime of device. So now the question is, what is the fatigue lifetime damage? Once the mechanical structure subjected to the cyclic load, they will be broken in some time. So during the large number of the cycle, first, the microscopic crack will be happening for the structure, and by increasing the number of the cycle, the size of the crack will be increased to the macroscopic, and by further increasing the number of the cycles, finally the cracked component will be broken. As you can see in this figure, there are 2 separated parts finally. So the fatigue damage is not only for mechanical structure, also it's possible that happen for the electronic component. For example, in this recent study, it is demonstrated that the power transistor characteristic will be degraded after certain time, as you can see here. By investigation of the structure, we can see this degradation happened because of the crack. So let's back to the energy harvesting and the fatigue in the energy harvester. Normally in the energy harvester, we have a simple cantilever like this, and then we apply the cyclic load. By applying this cyclic load, actually we can generate the power. At the meantime, this generated power, this cyclic load also is the source of the fatigue lifetime damage. So there are many different to estimate the lifetime of mechanical structure. One of the simple method, and of course accurate one, is the Coffin-Manson method. The Coffin-Manson method can be presented by this equation. Based on this equation, we can see that NF, the number of the cycles, is the function of the stress amplitude, fatigue strength, and of course the fatigue strength exponent. For each specific material, the fatigue strength exponent B and the fatigue strength are constant. So for example, in this study for the silicon wafer, it's already these parameters have been measured, and then so we have no control on them. So the only way to increase the lifetime of this based on this method is reduce the stress of amplitude. However, in the energy ambient vibration, in the energy harvesting, we have no control on the amplitude of the vibration. So the only way to reduce this stress amplitude is the change the geometry. So for this reason, we proposed a new geometry to reduce the stress concentration. So in the conventional piezoelectric MEMS harvester, we normally use the simple cantilever. You can see here, this cantilever is integrated with the one proof mass. So the concentration stress in this type of the structure is the anchor region. So to remove this stress concentration at the anchor, we came up with this curve-shaped anchor geometry. Actually, in here, as you can see, instead of using the straight anchor region, we use the curved, and it is the clamped to side. Further, we use the one proof mass at the center of the anchor, which is cancel the stress in this region. So by taking a look at this structure, we can see actually we expand the anchor region. So by expanding the anchor region, we can provide a uniform distribution across the cantilever. So let me show you some result. First, I want to show you the stress distribution in the conventional harvester. As we expected, we got the stress, maximum stress at the anchor region. However, if we take a look at our proposed curve-shaped one, there is a uniform stress distribution across the anchor. So in 2012, introduced the fatigue module, and we use this module for our fatigue assessment. In here, you can see under excitation of 9.5 millinewton, the conventional harvester will be broken because actually here the red color represents the size of the crack. You can see there is a huge crack in the conventional one. However, after, with the same amplitude of the force, there is no obvious crack in our curve-shaped harvester. By increasing a little bit amplitude of the force to the 10.5 millinewton, we can see the initial crack will be happening on top of the anchor. So as we expected, we cannot see any crack on the anchor region. So again, we did the fatigue lifetime assessment. So here you can see the fatigue distribution for the regular cantilever. We excite this one by the 2.5 G acceleration. That's gonna work for only 1 minute. However, in all devices or in all proposed structure with the same amplitude of the excitation, it can work for the 25 minutes. So it can be said that we actually increase the lifetime 25 times. So since we are interested to investigate the device experimentally, we use the MEMScap. This is the available commercial micro-fabrication process. Here we have a 400 micrometer silicon as a proof mass. On top of that one, we have a 10 micron silicon beam. On top of that one, we have a half micron aluminum nitride. And then on top of that one, about 1 micron aluminum is the top electrode. So we fabricated two devices. One of them is the conventional one. You can see the optical image of these devices, and another one is the curve-shaped one. So first, we measure the frequency response of the devices. This one represented for the frequency response of the conventional one, and however, the red color, this figure represents the frequency spectrum of the curve-shaped anchor. So here, two important things actually happen. You can see the curve-shaped, by using the curve-shaped, we are able to reduce the resonant frequency in compared to the conventional one. Also, the amplitude of the harvested voltage is increased. So all the data are summarized in this table. So the first thing that happened, of course, by curve-shaped, we increased the failure first. And then the good thing that we got it is we reduced the resonant frequency, which is desirable in the MEMS devices. And then actually we increase the harvested voltage. Once we talk about the energy harvested, we are interested to know the capability of device in terms of the generating power. So the generated power by curve-shaped anchor, you can see, can be increased more than 2 times. So in order to compare the two different structures, we normally use the very standard metrics, and that one is the normalized power. So also the normalized power density shows that we got the improvement by the curve shape. As already we talked about, the lifetime also in the curve shape that can be increased. So this is the snapshot of our devices. After testifying for a long time, you can see it was broken from the top of the anchor, and this one is actually predicted by our simulation result. So let me conclude this talk. First, we investigate the lifetime based on Coffin-Manson for the piezoelectric harvester, and then we propose a new structure for reducing the resonant frequency, increasing the power density, and also enhancing the lifetime of the device. So based on the FEM and experimental result, we demonstrated that by using the anchor shape, we are able to get the more idle energy harvest. So thank you so much for your attention. Now I'm open to your questions.